Hello everyone, I am Sandeep Kushwaha
and myself Harish Yadav.
and we are explaining in our video our topic transport analogies.
So transport analogy help us to draw the parallels between heat transfer, mass transfer and momentum transfer. So moving to the questions. So our first question you can see on the screen. You can see question on the screen. You can pause the video and give it a try. Now let's start the question.
We are given a situation where a liquid flow over a flat plate of length L and we have in question Reynolds number which is 1400. We are given a situation where a liquid flow over a flat plate of length L and in our question Reynolds number at length x equal to L is 1400 and Reynolds number is explained as, so the Reynolds number at length L is explained as rho u infinity L by mu, where rho is density of fluid, u infinity is free stream velocity, L is defined as characteristic length and mu is viscosity of fluid.
Now we are told that surface concentration CAS is greater than bulk concentration CA infinity, which suggests that mass transfer is taking place from the surface of the plate to the bulk. And also we are given that surface of temperature TS is greater than bulk temperature T infinity. That suggests that heat transfer is also taking place from surface of plate to the bulk of fluid.
So our goal is to find Nusselt number and friction fanning factor at x equal to L.
So let's start the solution. Given we have given Reynolds number at x equal to L, 40 CAS concentration at surface greater than concentration at bulk. Temperature of surface is greater than temperature at bulk, and Prandtl number equal to Schmidt number equal to 1, and at x equal to L, del C star on del y star equal to 13 and y star equal to 0, where CA star is concentration difference with concentration difference of bulk and at surface, and y star is equal to y by L.
As per the problem statement, we have to find Nusselt number at x equal to L and friction fanning factor at x equal to L. So we will write to find. So as per the problem, we have to find Nusselt number at x equal to L and friction fanning factor at x equal to L. So we will write our problem statement. Not problem statement, find Nusselt number at x equal to L and friction fanning factor at x equal to L. So we can do this problem by using transport analogies because it relates the principle of heat, mass and momentum transfer. So here, as we have Prandtl number and Schmidt number is equal to 1, so we will use the Reynolds analogy. As we know, we have given a flat plate of length L. We will consider fluid flowing in x direction and its vertical direction is y, and the hydrodynamic boundary layer is like parabolic. Velocity profile will vary like this. Surface concentration as Cs and temperature Ts, and we have considered bulk concentration as Ca infinity and temperature as T infinity.
We have steady state and all the concentration Cs, C infinity are constant. Temperatures are also constant. Now we are given that x is equal to d c upon dy. So now moving further, y star is equal to y by L from the questions implies that y is equal to L into y star. From here we have dy by dy star is equal to, and now d c star by y star can be written as dc star upon dy into dy by dy star. This term is equal to L, so we can write L into d c star upon dy. Now c star is equal to Ca minus Cas upon Cn infinity minus Cs. Differentiating C star, putting C star into this equation will give d C star upon R equal to L into d by dy of K minus Cas upon C infinity minus Ca. Since numerator of this equation is a constant, we will take that out, and the Ca is varying with time. Sorry, Ca is varying with distance, so that cannot be, that will be different. Since numerator part of this equation is constant, so we will take that out, and our equation comes out as dc star upon dy star is equal to L into 1 by C infinity minus Ca surface into dCA upon that y star equal to 0, y will be 0. So dCA star at dy star at y star is equal to 0 is equal to 13. So this equation will L by C infinity minus Cas into dCA of dy. From here we will have dCA upon dy at y is equal to 0 at 13 into C infinity minus Cas upon L. After solving, we have got this equation taking its simple. Also, from this we can rearrange dAB by Kc. Now we know that Servo number is equal to Kc into characteristic upon B. So from rearranging this equation, we will get Kc into L upon dAB equal to getting F by 2 into the number with Servo number. We will get F is equal to Servo number into the number by 2, which is 13 into 1400 divided by 2. Now from here we will obtain F is equal to 2 into Servo number divided by the number. This will give 2 into 13 by 1400. On solving this, we will get value of x, which comes out. So,
Like-
so we will get x is equal to 0.01857. So this is our second answer, that is fraction factor at x is equal to value.
Now moving towards the next question. Here we have some data, and firstly we will know about the question. We have given an experiment in which water flows through a cylindrical pipe and it evaporates in air at 25 degrees Celsius temperature. We have given some data. Here WL upon PA minus WL upon PW minus PA, which is equal to 3.17 into 10 to the power 8 minus 8 UL to and PA bar pressure of initial water in air stream. And U is defined as velocity of air stream, which is in centimeter per second. In this question, we are asked to transform this equation into a dimensionless form, specifically involving the Reynolds number based on cylindrical length. The system involves air as the gas and water as the evaporating substance, and we are given the properties like density, viscosity, and diffusivity. So the goal here is take the empirical equation and express it in terms of dimensionless group such as Reynolds number, Schmidt number, or Sherwood number. This is a classical dimensionless analysis and correlation derivation task. Now, in the B part, we apply the relationship to a real situation. We have a naphthalene cylinder exposed to flowing stream of pure CO2 gas at 100 degrees Celsius and 1 atm pressure. The cylinder has a diameter of 0.075 meters and length L is equal to 0.6 meters, and the CO2 is flowing at 6 meter per second. We are given physical property of CO2 like density, viscosity, and diffusivity, the vapor pressure of naphthalene, and it's stated that the partial pressure of naphthalene in the gas is 0, which makes it a dilute system. Our task to use the same kind of relation from part A to calculate the rate at which naphthalene sublimates and express that as kilogram per hour.
Now moving to the B part of the solution, we have given system. We have given water air system. Molar weight of air as 29 gram per mole. 8314 into, we are given temperature at 25 degrees Celsius, and after converting it into Kelvin we will get 298 Kelvin. On solving this expression we will get rho as 1.1857 kg per meter cube. We have got two values, and now we have also given viscosity mu is equal to 2 into it is given by mu CO2 upon rho into d a b, which will be into 10 power minus 0. So, starting the solution from the A part. In the first part, we are asked to derive a relation JD as function of Reynolds number at length L. We have formula JD is equal to Stanton number for mass transfer into Schmidt number power 2 by 3, which is written as JD is equal to Stanton number for mass transfer into Schmidt number power 2 by 3, where Stanton number is where Stanton number is given by mass transfer coefficient into pressure into average mass divided by density. Reynolds number be a function Reynolds number power n. Extending this, we will get V into L into U into rho upon mu power n, taking it as equation second. Now from equation 1 and 2, we have Stanton number is Schmidt number power 2 by 3 is equal to V into rho u L upon mu power n. Substituting the value of density into viscosity into Schmidt number P rho u L upon mu power n. Now rearranging this equation, we get kg equal to V into minus 8 into u L power 0.8. Now we know that W is equal to Na into molar weight, which will give kg into mW into Pw minus PAR. Now substitute after solving this equation, we will get the value of constant x, and from there we can determine the value of phi REL is equal to V into REL power n.